Okay, so we're going to go over, in this class, we're going to go over ideal gases and liquids. So that's going to be today. And then for the next class, we're going to go over non-ideal gases, including some equations of state, like van der Waals and others. And then also looking at reduced pressures and temperatures and compressibility charts. Okay, and then in Chapter 6 is just looking forward. We're also going to go over vapor pressure, humidity, Raoult's law, bubble and dew points, and then solid, and liquid systems. Okay, so let's just talk today about this ideal gas law and liquid densities, especially mixtures. I'm just going to highlight a couple things that are going to be really important with this lecture when we get to them. So let's just go through this. Ideal gas laws, the standard conditions, and then ideal gas mixtures, including discussion about partial pressures. Okay, so this content is quite important. This is really foundational for a lot of the material that we're going to be covering later. Okay, so let's just do some thought experiments here. If I have 30 kilograms, let's say it's 30 kilograms per minute that's coming in, and there's no accumulation. Okay, so it's just it doesn't build up or decrease in there. Can I have 20 kilograms per minute coming out? And the answer is no, because we have a mass balance. The mass coming in is going to have to be equal to the mass going out if there's no accumulation or generation or consumption of mass. Okay, now let's think about moles. Is the following possible, where you have 30 moles coming in and then 20 moles at the end for this system? And here we have, yes, it is possible. Now we could have reactions taking place that are going to change the number of moles for this system. Okay, now if we have no chemical reactions, is this going to be possible where we have 30 centimeters cubed per second coming in and then 20 centimeters cubed per second leaving? Is that going to be possible? And yes, it is, because we can compress. For example, if it's a gas, we can increase the pressure and have it occupy less volume. Okay, now let's think about the possible with a mixer and no reactions. Can we have 20 centimeters of A coming in and 40 centimeters cubed of B coming in, and then have 55 centimeters cubed of the mixture? Even if we don't change the pressure, this can still happen because of non-ideal mixing systems. Okay, so you could actually have the mixture occupy less or more volume than the summation of the pure components. Okay, and so we want to be able to figure out with densities, how many units of mass per volume, or moles per volume, we're going to occupy with these. Okay, so we can't normally measure density, for example, but we can measure other quantities and then relate it to densities. Okay, so let's look at liquid mixtures now. In general, the liquid volume is not conserved, and so this is that excess amount. So we have liquid mixture of 1 plus liquid mixture volume of liquid pure component 2. Okay, and then that's going to have a different volume for the combined. And there's interactions that occur between like and unlike molecules that make this VE non-zero. In this course, though, we're going to assume that for like liquid mixtures, this is going to be equal to 0. Okay, so we're going to just assume ideal mixing between liquid mixtures. Okay, and so we can use this equation right here to come up with the density of the mixture. Okay, is going to be equal to the summation of the mass fractions divided by the individual densities. Okay, so why do we do it that way and not this way right here? Okay, so we don't do it that way where we just sum them up by the weighted fraction of the mole fractions. Okay, and so we don't do it this other way. Okay, So let's just look at the units of the equation. Okay, so in this case I have kilograms per meter cubed. Okay, and this is going to be kilograms of I divided by the kilograms of the mixture, and then divided by kilograms of I divided by meters cubed. Okay, so those two are going to cancel, and then we're going to have kilograms per meter cubed for the mixture. Okay, so let's just do a quick example here. What is the density of a mixture containing 20 weight percent A, and the rest of it is going to be B? Okay, and so we have row A and row B. So we just use that formula that we showed before. Here's our 20%, and there's our 80%, and then we have the densities that we have to plug in here. Okay, and so that's going to give us an overall density of 1.67. Okay, so that's how you combine densities for mixtures. But if you used this formula, then you got 1.8 grams per centimeter cubed, and that is not that's not the correct way to do it. Okay, so let's talk about gases now. Okay, so we're going to use equations of state. Maybe the simplest one is going to be this ideal gas law. Okay, so for ideal gas assumptions, we're going to use this, but there are many different types of equations of state that we can use. We're just going to cover a couple of those in the next lecture, but in this lecture we're just going to focus on ideal gas. So this is the main equation with the ideal gas law. PV equals N times R times T. Okay, so P is this is going to be the pressure. That's the volume in meters cubed. There's your moles. That's an ideal gas constant. Okay, and then you have the temperature. That's going to be an absolute temperature in Kelvin or Rankine. Okay, this is also an alternate form that you see many people write it in, and that's just because I've divided over this N term. Okay, so the N term that we divide over here and then make that V hat equals V divided by N. And so we call this a specific volume. That's like a meters cubed per mole. So how many meters cubed does a mole occupy for that gas? Okay, now assumptions with the ideal gas law: no interactions between molecules, and then molecules also have zero volume. Okay, so if I have really high pressures, then the assumption that there's no interaction and zero volume for the molecules themselves, that isn't going to be correct at really high pressures or really low temperatures. So the ideal gas law, okay, is going to be best at low pressures, okay, and then high temperatures. Okay, so so if we have, this is a P times the pressure times specific volume over pressure. For ideal, it's going to be on this just this value here, but real gases are going to deviate from that. So as we increase pressure, at a certain point you're going to have a gap here between what was the ideal gas law and the real gas. At a certain point that becomes significant. It becomes large enough that we need to take it into account. Okay, so here are just some general rules of thumb. You know, ideal gas law, you can use that for diatomic gases. Okay, so O2, N2, and such. When you're greater than 5 liters per mole for the specific volume. And if your other gas is greater than 20 liters per mole. Okay, so this one, at higher pressures, you can use ideal gas law. For this one, it just has a little bit lower pressures for the ideal gas law. Okay, and then ideal gas constant, this R value in our ideal gas law. There's different units for it. It's going to be the same values. In mechanical engineering, if you use a mechanical engineering textbook, just watch out. The molecular weight of the species, it may be included, so there might be a different value of R for each species. Okay, so this is the chemical engineering way of doing it. This might be a mechanical engineering way. Okay, here are some ideal gas constants used by units. I typically just go back to this one in SI units or this one in the energy equation. So one way that you can think about this is PV equals nRT, and then I'm just going to solve for R, and it helps me remember the units on this over NT. So I have my pressure in pascals, my volume in meters cubed, my moles there, and then my temperature in Kelvin. Okay, and so that's going to be 8.314 meters cubed pascals per mole Kelvin. And that's also equal to joules per mole Kelvin. Okay, so here's just a CRC handbook. Okay, so this is values of R, and you'll see just different values of R given different units right here. I typically just always start with the SI units and then convert those over anyway. Okay, so here's concentration. So we have our PV equals nRT. Okay, and then if I just want to get moles per liter, that's just going to be N divided by V, and that's going to be P over RT. So that's going to be a concentration. But if it's just the concentration of a particular compound, okay, let's say it's Na, okay, or Ni, I'll put Ni there. Okay, then I can multiply by the mole fraction and the total pressure. Okay, and that will also give me the concentration of that gas. Let's say it's in a mixture of gases, then that is this concentration form that's just specific to one species. Okay, so density, the density of the gas, okay, that's going to be mass, okay, mass divided by volume, not the moles divided by volume. So in order to get in that, we're just going to go ahead and multiply by the molecular weight. Okay, so if we just take our concentration and then multiply by the molecular weight, then that's going to give us a density. Okay, so that's just one way to get concentration or density for the gas. Okay, so let's just go through an example problem here. Suppose the tires on your car are inflated to 32 psi-G, that's gauge pressure, at 25 degrees Celsius. What is the tire pressure at negative 10 degrees Celsius? And assume that you're at sea level, okay, and would this make a difference in your answer? Okay, so let's just, we know that the moles, when it's hotter or colder, it's going to be the same number of moles in your tire, okay? And so we can just say that N equals, and then the first conditions, the P1V divided by R T1, that's going to also be equal to the number of moles in the second state, which is P2V over R T2, okay? So this just reduces down to this equation right here. Okay, so this is going to be a time saver. Okay, so if we do the calculation here, it works out to be 26.5 psi-G. So we started with 32 psi-G, and as the temperature dropped, we went down to 26.5 psi-G. Okay, so let's just see, if the atmospheric pressure were lower, okay, well, let's say we were at higher altitudes, then then that means we would be at that absolute pressure, and then it would be this final answer for the pressure, so just a little bit higher, okay, because we have so just in the calculations you got to make sure you convert between absolute and gauge pressure. Okay, only take ratios of values in absolute units. Now this is really important in the PV equals nRT, that you don't do degrees Celsius or something like that. You want it to be in Kelvin or degrees Rankine. Okay, so in absolute conditions, and never use gauge pressures. Okay, so if this is psi-G, make sure you convert that to psi-A, or better to maybe pascals first. Okay. All right. So standard conditions. So this provides a reference point for reporting gas flows. So here are just some standard conditions. SI standard conditions, 0 degrees Celsius or 273 Kelvin, 1 atmosphere pressure. There's a volume for your gas. You may have seen this one, 22.4 liters per mole for your gas for the specific volume. And then N is going to be in gram moles. Okay, so this is a little bit different in American engineering units. The temperature is 492 Rankine, 1 atmosphere. There's your specific volume, and you might use pound moles instead of gram moles. Okay, and then SPE, or Society of Petroleum Engineers, again, they just have different temperatures. And pressure units, same pressure there. Okay, so this is going to be used in our book a lot, the 22.4 liters per mole. Okay, so here's just a couple other definitions here. Gas flows. Here's a standard cubic meters in STP, those conditions that we just mentioned, the pressures and temperatures. Here's a standard cubic feet. Okay, and then these are just per minute, per hour. Okay, feet or meters. And then you might have standard cubic centimeters per minute. Okay, so these are just some abbreviations that you might see. And that helps you normalize these, so if the temperature of the gas changes, you don't get maybe a different flow condition. Okay, so here's some ideal calculations just to get back to standard conditions. Okay, just like we did with the pressure in the tire. Okay, I'm just going to breeze over this pretty quick. If you need to get back to standard conditions, you can use some of these. A couple examples. Standard. This is liters per minute, and rotometers. Standard liters per minute. So the value that you read there, okay, that's going to be in standard liters per minute. You might have to convert it for different temperatures. Okay, now you have a flow rate of a stream at 285 degrees Fahrenheit and 1.3 atmospheres is measured with an orifice meter. The calibration for chart of the meter indicates that the flow is that, okay, 3.95 times 10 to the 5th standard cubic feet per minute. So calculate the true volumetric flow rate of the stream. Okay, so what we want to do is, it's that many cubic feet per minute, but we want to do a temperature and pressure correction for this. Okay, so here is the new value. So we read this amount, but this was the amount that should have, with the correction. Okay. Okay, so let's get on to partial pressures. Okay, so what we define as a partial pressure of component A is a pressure total times its mole fraction in the gas mixture. Okay, so you have a total pressure. Let's say you have a gas mixture at 1 atmosphere, for example, but you have 21% of that is going to be O2. So the partial pressure of O2 is going to be 0.21 atmospheres. So it's how much of the pressure is exerted by that species, for example. Okay, so that's where this example was, sea level, what is the partial pressure of O2? Okay, and that's going to be 0.21. Okay, so let's just go with ideal gas mixtures. Let's say we have gas composition coming from a well in Wyoming, a natural gas well. And let's say that's 70% CO2, 25% methane, and 5% H2S. If the total pressure in the well is 20 atmospheres, what is the partial pressure of CH4? Okay, so let's just use our equation that we had. It's just going to be the mole fraction times the total pressure is that partial pressure. So that's going to be 5 atmospheres partial pressure for the methane. Okay, so here's ideal gas mixtures. And this is a law that says that the partial volumes add up to the total volume. Okay, so you can think of it like the volume occupied by one species. You can add all of those up together to get the total volume. Okay, and it's very similar to this partial pressure idea, where the volume fraction of a particular species is just the mole fraction times the total volume. Okay, so here is one problem. We have nitrogen, okay, coming in, and we have volume of 2 meters cubed, and the pressure is 10 centimeters water gauge, and you have a temperature of 200 or 25 degrees Celsius. Let's say you wanted to replace the volume every 5 minutes. So we need to calculate the mass flow rate of nitrogen using the ideal gas equation, and then calculate the mass flow rate of nitrogen using conversion from standard conditions. Okay, that way it's just a little bit confusing for problem 5.9 for your homework. And then here are some other homework hints. Okay, this is going to be 5.12. You have gas cylinders. Remember that total mass is the mass of the tank plus the gas, and then the mass of the gas is the moles of the gas times the molecular weight of the gas. Okay, and then with constant volume at standard temperature, pressure, moles equal constant. You use the workbook for 523. This is the breathing one. It's kind of a fun example, and then there are some additional hints that are given here at this address. Okay, so that ends the discussion today for this. Just in review, we talked about the density of liquids and how they mix. Okay, and then we also talked about ideal gas law and when you can use ideal gas law, and just some brief examples, standard temperature and pressure correction for gas flows.